Thank you very much. My name is Ryota Kanai. I'm the founder and CEO of the company called Araya. And what's unique about us is as a company, we actually study consciousness. Probably you don't see consciousness startups anywhere else. And so today I want to talk about consciousness and AI. And oops, Okay, so this is the kind of thing we're interested in at Araya. So normally, from a scientific viewpoint, we tend to distinguish consciousness and intelligence, but we are trying to make some connections with, by thinking what kind of functions consciousness have. And of course, there might be some philosophical point of view to think maybe consciousness has no function, but I believe there might we gain new insight into consciousness just by thinking what consciousness is good for. And also as a company, we do like normal AI developments, and also we work on very much interface. And we have about like 20 full-time researchers at the company, and one of the guy on the left side, Shunsa side, he used to be a postdoc in Julius lab, and also we used to have Masafumi Oizumi, who was the first author of IIT 3.0. So I keep stealing people from Julius lab and then work on consciousness in my company. So yeah, okay. So the motivation of this talk and my research in general is what is the relationship between consciousness and intelligence. So when I talk to like investors, they ask why we should understand consciousness. Of course, there are the clinical reasons, but also I believe we can actually make AI better by trying to understand consciousness. And also, there's a kind of inverse relationship, which is by thinking about how to implement consciousness in AI, we can actually refine ideas that already exist in consciousness research. So like consciousness has a very long tradition, like in philosophy and also cognitive science. But a lot of times, some ideas in theories of consciousness tend to be kind of vague. But once we start thinking how we may be able to translate them in AI or mathematics, then we have to refine a lot of concepts. Yeah, and so and similar to consciousness research, intelligence is also very hard to define. And so I give a tentative definition of general intelligence, which is the ability to solve multiple problems, tasks efficiently, including novel tasks using existing knowledge of the agent. So, and I propose there are at least 3 ways to achieve this kind of general intelligence. And of course, you may have other types of definitions of general intelligence. A lot of times people compare intelligence to human-level intelligence, but on the other hand, human-level intelligence is not an operational definition. So I just stick to like very simple definition of something similar to transfer learning. And so I've been trying to make connection between existing functional theories of consciousness with potential implementation of general intelligence. And so this is the list. But today I want to mainly focus on the thing related to the global workspace theory. But recently we published this paper with Asa Giuliani sitting over there, where we try to sort of translate these 3 ideas in consciousness research into potential implementation. And so this is a kind of long review where we draw the parallels between the 2 fields. And so, as I said, I want to focus on global workspace, at least for the first half of this talk. And so the idea is something like this. So when we develop deep neural networks, usually we build just one function, so input-output relationship. So the most typical one is the input is an image, and then you get a label for categories. So put an image on cat, and then the output is cat, the word. And actually, like in our business, we develop many neural networks for our clients, but we can create new neural networks by combining different networks. So, for example, of course, so here, like each arrow corresponds to a deep neural network, but then if, well, for example, like you can take an image of a cat and then translate it into the type or what kind of object category, and then we can also convert that word to the speech sound or maybe translate into a different language. So, so basically, once we have like many neural networks to solve individual tasks, then we can combine them to solve new tasks. So basically, it becomes just a pathfinding on the graph. And so that seems to be actually happening in the brain, or at least that's our claim. So what's different between artificial neural network and the brain is, in the brain, like, there are many, many connections. So there's no single path, but there are many branches, and you can go, between different brain regions. And there is and then the flow of information in the brain seems to be modulated by the inputs from the area called the thalamus. So in the cognitive neuroscience, it's basically attention to route inputs to the different parts of the brain. And that seems to be done with different oscillations like alpha frequency. And once we have something like that, to solve a new problem, we can sort of create a new network on the spot inside the brain. So maybe through the influence from the thalamus. And so, but this is now getting very similar to the theory of global workspace. So the idea is like this. Bruno and Mario yesterday already talked a bit about global workspace. But the idea is, okay, we have many specialized functions in the periphery. So like each network can do some sort of maybe speech recognition, object recognition, and so on. But the idea of global workspace theory is the result of the specialized module is shared across like different modules through broadcasting of information. So then the agent, humans or animals, can use that information flexibly. So that idea is very similar, and there have been a lot of studies to show that the frontal and parietal regions in the brain correspond to this global workspace. But what's really frustrating to me, maybe some other people, is that maybe this is not like really a theory of consciousness, because it doesn't. A lot of ideas are kind of vague. What does it mean to broadcast information, share information across different areas? And also, I think a theory of consciousness needs to be able to tell whether some system is conscious or not. So, let's say we have some artificial neural network. How can we tell which part of the network corresponds to the global workspace as a kind of intrinsic property of the network? So that's the frustrating part. And also, we have only intuition that it's useful to share information, integrate information. But what kind of function do we gain by having this kind of architecture? And yesterday we heard about this new the conscious Turing machine idea. So the interesting thing about this is it gives us more of an operational definition of global workspace. Actually, the idea is more high level, so it's independent of individual like implementation. So it can be applied to machines or the brain, but I think it's useful to have like explicit representation of the general idea. And yeah, so and also like when I was reading this paper, I felt this is something we can implement with modern neural networks. So multimodal neural network with a lot of transformers for attention, then it seems like a really straightforward to think. So I think it's really like this could be like a nice inspiration for like AI engineers. And also in AI field, especially Yoshua Bengio is a very prominent figure, but he had a paper called Consciousness Prior, and then more recently he had like several lines of more like experiments that show the usefulness of shared representation. So the idea is again similar. So you have like many specialized modules, but then you can insert this orange slip, which is kind of basically shared representation across different modules. And then actually having that kind of representation is a very useful way to coordinate a system consisting of multiple modules. And also, we took another architecture called Perceiver to implement Global Workspace. So Arthur Giuliani has a talk after this session, so if you're interested in the details, then please come to the talk. And also another interesting parallel between AI and neuroscience is that in AI research, it's very common to sort of consider neural networks in terms of encoder and decoder. So, for example, typically, you use some input, and then this network needs to learn to reproduce the input. So this sounds like a really trivial thing, but it has to go through some bottleneck in the middle. So that means this network needs to learn to compress the information efficiently and then reproduce the output. And so, yeah, so that way, this network needs to learn some sort of like important features in the training data set. And in the brain, we have something probably similar, and then you might have heard of predictive coding or free energy principle. And basically, the loss function for free energy principle and the so-called variational autoencoder are identical. And then, and also predictive coding is one potential implementation of free energy principle. And some neuroscientists think we may have this predictive coding framework. So how it works is the bottom-up input is kind of compressed as you go deeper in the brain, and but by sending prediction error, which is the so basically, like deeper areas send predictions about what's coming next, and then the discrepancy between the bottom-up input and the top-down prediction is kind of is the bottom-up signal. So prediction error is a bottom-up signal. So this corresponds to, again, the encoder versus decoder distinction. So in the brain, we have so the bottom-up signals encode the information for high-level representation of things like category of objects. And then these top-down signals correspond to the decoder. So basically, it tries to reconstruct what's coming next. And so today I'm not going into details, but we are thinking maybe this decoder part corresponds to consciousness, because in the brain there is some empirical evidence suggesting that top-down signals are like a really crucial part for generating consciousness. So normally when we see a new image, then it triggers a wave of bottom-up input. And then actually the brain managed to process a lot of information, but that seems to happen unconsciously. And the consciousness happens when the feedback goes back to the early visual areas or other early sensory areas. So that's an interesting thing, and I'm thinking maybe there's something special in this decoding process. And if we think the brain as a bunch of autoencoders, then we get a view like this. So, okay, we have like many input coming from the different modalities, and then they are like represented like in a more abstract way at some point. And then it doesn't have to be just about sensory signals, but they could be also connected to like other output-related regions. But the important thing is, as I showed you with this kind of diagram with arrows, to make these networks work together, we need to have some sort of shared representation. And so in this case, these are all different latent spaces, so we can train different networks independently, but then they have to speak the same language. So according to conceptual machine, that might be the brainish. So this network needs to learn to sort of communicate with each other. And so this could be done through by learning contingencies, so if you watch a lot of videos with sound, then at least you can train the network to learn the correspondences. But that's not the only way. Yesterday in Ariel's talk, he talked about this kind of alignment of representations. So we're thinking maybe in the brain we may also align latent spaces in an unsupervised manner. So he explained this briefly yesterday, but the idea is, okay, so let's say you have a neural network to encode a lot of French words just by reading a lot of French text, and then another network that learns the representation of a lot of words in Japanese. And then even without dictionary, by finding the right coordinate transformation, we can find reasonably good correspondences. So that's unsupervised learning, which can be useful in machine learning. But I think what's interesting to me is that we never thought this way in neuroscience. So for example, yesterday we heard about synesthesia from David Eagleman, and it's been really mysterious why a particular digit acquires a particular color. He showed that maybe children may have learned from some colored blocks of letters, but yeah, but in synesthesia, this kind of idiosyncratic matching happens for some mysterious reason. But we're thinking maybe the brain tries to align latent representations across different modalities all the time. And so that might be an explanation for why we have synesthesia. And so, for example, for numbers, we may have some sort of representation of numbers in kind of abstract space, but we may also have abstract representation colors. And they may not correspond perfectly with each other, but if there are similarities, then we can find mapping between them. And then we can use that to make some sort of analogy. So when we talk about experiences, we always relate our specific experiences to some other things, maybe we can talk about sound or taste in terms of shape and things like that. Well, it's a metaphor, but maybe that's achieved through some sort of alignment in the latent space. So we reinterpreted global workspace in terms of shared latent space. So of course, so in my opinion, the theory of global workspace never explicitly mentioned anything like this, but if we interpret global workspace as a shared latent space, it kind of sort of makes sense, and also it makes clear what the functional gain is by having global workspace. And here I added not just sensory processing, but you can also embed tasks. In neural network research, there are a lot of attempts to encode and represent different tasks. And also world models play an important role. So when you have a good world model, you can use it to gain sort of predictions about the future. And then you can run mental simulations. So that's very useful. So, okay, let's see. Okay, yeah, we have been looking for a global workspace, using fMRI, but I'll skip these. But we also tried new experiments with inspirations from this kind of interpretation. So basically, we look for brain region that shares information with other places. So I skipped the details, but the main result is that basically, as predicted, normally we get the frontal and parietal regions seem to share a lot of information with other regions. And also, as I mentioned, we do brain-machine interface development, and we recently got a huge grant from the Japanese government to develop new brain-machine interface. And of course, brain-machine interface can be used for speech generation or to control remote robots. But our secret plan was to build brain-to-brain communication. But here, again, the idea of connecting latent space becomes very useful. So normally in a typical communication, we encode some information, and then it's converted into some thought in our latent space. Then we use that information for speech, and then we can communicate. And the other person needs to re-encode that information to understand what the other person is saying. So in a way, language might be a kind of proxy for our latent space, but we want to connect latent spaces of two people or two animals directly. And to do that, again, we are thinking about doing this kind of alignment. So nowadays it's really straightforward to predict what the monkey is seeing by recording the neural activities. But we want to create an artificial shared latent space between two monkeys through this kind of alignment. So the idea is whenever we want to decode the mental image from new animals, we typically need a lot of new data. But what we are doing is basically doing transfer learning to a new animal. So basically, we want to be able to tell which neuron corresponds to the representation of an apple just by looking at neural activity. So that's the motivation. And yeah, so we are doing this kind of experiments, but so far we have just done it in a kind of AI version. We trained two different networks, and then showed that we can basically sort of transfer the image from one network to another. So that's just a proof of concept, but eventually we want to do this in real animals. And also, these experiments are motivated by these famous Hogan sisters. They were congenitally connected through the thalamus, and apparently they are having a lot of anecdotal reports that they can share qualia. And so I thought, okay, maybe this might be a good way to test whether AI or some machines have consciousness. Well, we can check whether a piece of machine has consciousness by connecting that to our own brain. So that was the motivation. So in a way, of course, there's no real systematic study on those twins, but we can, I think some anecdotal reports really defies our notion of privateness of consciousness, because if we have really high bandwidth connection, we may be able to share experiences. Of course, it's a bit unclear what it means, but this is a really interesting insight. Okay, so yeah, so far I talked about global workspace, and from here I want to talk a bit more about qualia. So I've been thinking how to explain what I'm doing, but I think this experiment is probably my original motivation. So some of you may know this experiment by Kanai, where they rewire the input from the retina to the auditory cortex. So it's a little bit complicated to explain in 2 minutes, but the idea is when you, okay, so there's a way to connect retinal input to the auditory cortex inference. So it's done even before birth. So all those animals develop to learn to use that information from the retina in the auditory cortex. And they did a very clever experiment to show that those animals seem to be feeling vision from the activation of the auditory cortex after rewiring. Maybe it's a little bit similar to sensory substitution David Eagleman talked about. So basically, the brain adapts to use information from any modality, and then that sensation seems to correspond to the type of experience. So if the input is visual, then we seem to learn to generate visual qualia. And in those animals, after rewiring, the typical auditory neurons have lateral connections locally, in the middle, but after rewiring, those previously auditory neurons start to acquire connectivity similar to the visual cortex, which is basically a lateral connection with distant neurons of similar orientation tuning properties. So that seems to somehow anatomically capture some important statistical features in visual input. So so I thought maybe we want to relate what kind of connectivities or we want to understand what kind of connectivities generate visual qualia or auditory qualia. And so in that context, I've been interested in IIT. So, as I said, my frustration with a lot of theories of consciousness is that they don't tell us whether some certain network is conscious, or they don't even tell whether certain network generates visual experience or auditory experience. So ideally, like IIT could give us an answer. So that was the original. Original motivation, and the ideal experiment would be we take the anatomy and maybe sort of functional connectivity in the auditory cortex and visual cortex. But if we want to apply IIT strictly, that we have to understand the so-called TPM at multiple resolutions in fine details. And then we want to compute phi, or information structure, based on the TPM derived from this kind of anatomical structure, and then compare that structure to qualia. So that's the ideal situation. But this is very difficult. So now it's getting more and more feasible, but it's very difficult to get precise connectivities from living humans. And also, computation of IIT is very hard. Usually, people deal with maybe a small number of units, and also we need to have some methods to make comparisons between those structures and reports of qualia. So these are all difficult things. So I want to simplify the problem. So the first thing is instead of looking at the real brain, we can use artificial neural networks. So we can train many neural networks just on auditory data or visual data to create artificial auditory cortex and artificial visual cortex. And then we know all the connectivity and weight. So that's our progress. And yeah, and the second problem is the computation of IIT. And I think there are two aspects to IIT. So there's a recent paper that proposed a distinction between strong IIT and weak IIT. And the idea is, so IIT has both mathematical and philosophical components, but then the computational integration is a kind of general mathematical framework, so you don't need to make a philosophical commitment to IIT, but you can use the mathematical tools coming out of IIT. So that's the weak IIT position. And so previously, we have been trying to find ways to compute phi. The version we were working on was IIT 1 and 2. So it's very from IIT 3.0, the framework has changed quite a lot. But we have been using kind of optimization methods to compute phi in systems. So at least now we can compute phi for a system consisting of maybe more than 100 nodes. And then we also found a way to compute the so-called complex in IIT 2, and then actually apply that to physiological data. And then so the video on the right is showing where we expect to see the complex or consciousness. So there is more concentration toward the back of the head. Yeah, but this is kind of good, but this doesn't tell us so much about the quality of experiences. So it only computes the amount of integrated information. So we have been thinking about kind of taking the philosophical aspect of IIT and then use different maths. So that's the idea. And of course, conceptual IIT is not a direct test of the IIT as a theory, but we want to use it to drive new type of experiments, new type of research. So one thing we want to do is the one idea we got from IIT is so whether a network produces visual or auditory experience depends entirely on the properties of the network. So if we know all the structure, weights of the network, we should be able to tell whether it's visual or auditory. So that's the motivation, and it doesn't really prove whether IIT is true or not. But I think similar approaches have been taken by people studying IIT. For example, you might have heard of the TMS EEG experiment where when people are conscious, the response after TMS pulse is like more complex and it's harder to compress, so meaning it's more complex. So you can use the measure called PCI to test whether someone is conscious or not. But if you think about it, it's just a complexity measure, so it's not the direct test of IIT, but I think it's a very original experiment motivated by IIT. So I think that's a meaningful direction, and so yeah, so this is one of such kind. So what we did, this is work in progress, but so we trained a lot of networks on 3 different kinds of audio tasks and 3 different kinds of visual tasks. And then they have all the same architecture, and they're all freely connected. And then what we did was to construct a meta network to predict for which task a network was trained. So basically, we wanted to tell whether a network is specialized in visual or specific task. And then what we got was this kind of confusion matrix. So basically, like visual networks are kind of confused and separate from the auditory network. So it suggests that there's something like something visual specific or auditory specific in the pattern of the weights in the trained networks. So instead of using IIT, so basically we wanted to capture the kind of like visualness or auditoriness in a network. So based on this shows that there some information is there, and probably this may reflect some sort of like invariances or equivariances. So yeah, so maybe yeah, so the invariance and equivariance are kind of similar concepts, but the idea is for visual images, okay, if you shift this image to the right, and then the application of the neural network on the same image is also shifted this way. So that's an example of equivariance for translation, but this kind of sort of equivariance is like unique to images, and also in the early days, convolutional neural networks were very successful in image recognition, and that comes from this kind of weight sharing of the kernel. So basically, a network is trained to do the same thing everywhere, and also there's a thing called Turing. So they together create this kind of translation equivariance. But we expect to see different types of equivariances for vision and audition. And so I predict maybe this meta network captured some of that. And yeah, so this is what we have been doing, and also this itself is a really interesting deep learning research topic. And yeah, so for example, instead of convolution, you can use a D group as a constraint for training. So that seems to make things more efficient. So and also we can use things like permutation equivariance, and there are many kinds. So maybe I hope that maybe some mathematicians could help me sort of use those concepts to understand the properties of neural networks. Yeah, and also we have been so this is just an example of first order autoencoder, but So in the previous setting, I used this kind of supervised version of the classification for different types of network, but we can embed a lot of neural networks by creating this kind of meta autoencoder. So basically the input is the neural network, and then output is reconstructed neural network, but we want to represent neural networks in this latent space. And yeah, then eventually, we can talk about how networks are similar to each other or clustered together. So yeah, but there's a related study on this. Actually, there are maybe a lot more, but in machine learning, there's a concept of meta learning, and this network from Max Tegmark's group some years ago basically encodes a task. So task is basically a lot of data about input-out relationship, and then encode it. So you have a representation task, and then this network learns to generate weight for this first-order task-specific network. So basically, if you consider this part as also encode, you could use this part to encode neural networks. Then you can have a kind of latent space representation of a lot of neural networks or a lot of tasks, and then then you can generate new networks, or you can also use that information to talk about whether two processes are similar, or maybe potentially you could do some sort of vector summation and things like that to generate new type of neural networks. Okay, but this has been really enlightening to me to think about what it means to have meta representation. So in consciousness research, there's something called higher order theory, and then the idea is that consciousness requires a meta representation, but it's been really unclear to me what it means to have a meta representation. So for example, let's say you have an input, and then there's a function, and then you get a vector. That's for first order representation. But you can add another function, but it's a bit strange to say that's a meta representation. But sometimes neuroscientists naively think it might be like that. But then we can have meta representation and so on. So that's not very good. But also in cognitive neuroscience, we often take confidence estimation as metacognition. And so we do some sort of first order judgment, and then typically we get some decision response, but at the same time, we can get some confidence estimation. But this is a very normal thing in computer vision, so people just take softmax, and so normally for any visual recognition task, we get some confidence estimation. So yeah, so if that's enough to make some machine conscious, all the deep learning will be already conscious. But this is the kind of metacognition, meta representation I think might be useful to think about. So basically, as I explained in the meta autoencoder, we can take so this arrow, one arrow is a neural network, and then we can represent each function in a different space. So that seems to be a better way to characterize meta representation. So basically, we want to convert processes or arrows into an object in a different space. So maybe mathematicians may find a useful way to formulate this, or it might be some trivial thing, or I don't know, it might be related to some category theory. So I'd like to hear if mathematicians have any ideas about how to handle this, or whether it exists. But I think this might be, again, related to qualia. So in the brain, we have many different neural networks, and then we can represent neural networks in a different space, which I call qualia space, but it's basically a function space. And then once we have this kind of meta representation, we can we can also encode filter that detects all the red stuff or green stuff. So they must have some sort of similarities in this function space. And also, I mentioned, I wanted to know whether or not why vision feels different from auditory experience. And so that difference should be also captured in this space. But but it's just a very kind of sketchy idea. But this may be a better way to characterize a higher order theory. Okay, and I have just one more topic, and I'm covering a lot of things, but again, so this is more a neurophysiological study. So again, like I'm just taking this conceptual IIT approach. So the idea is if connectivity is different depending on the specialized functions, then that difference may be captured by the signals for different brain regions. So basically, we take a single channel signal for like 20 seconds or 30 seconds, and then click on like speaker recognition neural network made of transformers. So this network is originally developed to distinguish different speakers. So that, we talk different things, but we can tell who's speaking. So there must be some sort of common features specific to the person. So now we take those electrodes as different people, and we try to predict which electrode we are looking at. So without looking at any relationships between electrodes, just one electrode in just 30 seconds. And then out of 60 channels, we can make a prediction about 30% of accuracy. So that's not 100%, but at least it shows that there is a signal specific to each region. So ideally, like we want to be able to tell whether the signal is coming from visual cortex or auditory cortex. And roughly, it seems like the distinction comes from like different parts of the brain. The frontal lobe and parietal lobe seem to share some features. And then temporal lobe and occipital lobe seem to share some different patterns. So maybe there's the broad differences between the cognitive function regions as opposed to like sensory regions. So but we want to go further into this. But it's still a preliminary result done by an undergrad intern. So it's a work in progress, but he's been doing great work. Okay, that's all. I'd like to have some feedback. Thank you very much.